So one of the things we've repeatedly seen with the progress in AI, that certain milestones really require a very high level of investment to accomplish a certain large engineering task. These things are very difficult, quite often quite difficult to carry out in academia. And corporations that can put together a teams of a few dozen people can accomplish things that are very difficult to do anywhere else. And in fact, IBM has, to me, kind of two incredibly important historical milestones in the history of artificial intelligence. 1997, Deep Blue beating Kasparov, and then again in 2011, the team that Watson that beat two expert players in Jeopardy. And unlike Deep Blue, which I think IBM had a difficult time translating into business, if you now hear IBM is about Watson and cognitive systems, and Dr. Guru Banavar is vice president in IBM Research, and he is with one leg in the research world, but equally involved in translating this technology and involved with different organizations in the business world, and he's going to tell us about it. Please.
It's great. Thanks a lot. Good morning. It's really great to be with this incredible group of multidisciplinary thinkers. Let me get that going here. So yes, thank you very much, Moshe, for inviting me and for that introduction. I would like to talk about the other half of the coin, the other side of the coin of AI that we've heard one side of today in the morning. That's sort of the physical world, and how do you manipulate and understand the physical world. Then there is the mental world, which is the cognition, where you need to do a number of very high-level processes. All of us do this regularly, and AI has been as much about understanding those processes of intelligence back from when we started in the mid-50s and throughout the last 60, 70 years, right, where we have continuously made progress. You mentioned two milestones, but even before that, from IBM, in fact, we've had other milestones such as playing checkers, having backgammon using reinforcement learning was another milestone in the mid-'80s, and then the mid-'90s, and then 5 years ago with Jeopardy. I think the Jeopardy milestone is particularly special because it breaks through into the domain of language, which is fundamentally what distinguishes us as a species from everything else, right? So that is the hardest problem, and there's so many different aspects of language that we still have not cracked, just to be very, very clear about it. But I think we've cracked enough of the issues with language processing that we are finding a tremendous business strategy that is currently active in IBM, and to the point where our CEO, Ginny Rometty, has basically declared that Watson and cognitive computing is the future of IBM. Just as much as the System 360 was back 50 years ago, a transformative system for IBM strategy, we think Watson is a similar transformation for IBM in the next several decades. So I'm hoping to give you a little view of what is going on commercially and what is going on the research side of Watson, which is done by an entire research division in IBM consisting of more than 3,000 scientists from 12 labs around the world and many academic partners. And I'm happy to say that Manuela is one of our academic partners with whom we are doing a number of research projects as well. And I also should say that Vijay, unfortunately he was not here, but he and I, the last time we were at the same conference together, we were actually physically mistaken for each other. People would come up to me and ask me a question that they meant to ask him. So you're kind of looking at is somebody who looks like Vijay, except I have blue glasses, I guess. He's got black. IBM, right? So I want to tell you the story of cognitive computing from an IBM perspective, which I want to kind of step back quite a bit and think about the history of our species, where we've always built tools to augment first our physical ability, to augment our social abilities, and now I think we've hit a serious cognitive wall, so to speak, just because of the amount of not only data, but the amount of knowledge that's around us. I read maybe 5 to 10 articles a week as a researcher. I would love to read 100. I would love for my doctor to be able to understand and read all of the clinical trials that have happened until yesterday, but most doctors are probably 5 or 10 years behind in just their understanding of what's going on in the world. So we have hit a cognitive limitation, and how can we augment our cognitive abilities through tools that we can build? That's the perspective through which I'm going to be looking at the entire presentation today. And so over time, we have, in fact, built a number of cognitive enhancers, right? And the reason we call this new era cognitive computing is because it's a set of computing capabilities that enhances cognition for humans. So the combination of people and machines to do cognitive processes together far exceeds, we believe, what either one of them can do by themselves. And when you combine the two, I think you come up with a new kind of expertise, which is, I think, the foundation for a lot of the work that we do in our knowledge economy. And therefore, I think it's very, very relevant to the future of work. And I want to talk about the technology itself and then talk about what impact is it having on professions that are absolutely based upon knowledge and cognitive processes. That's really where I'm going in this talk. But before I start on that journey, every time I give a talk like this, people ask me, so the Jeopardy machine, the Jeopardy show was in 2011. So what has Watson done since then? So let's ask Ken Jennings this question.
Hello, Kent Jennings. I haven't seen you since that TV quiz show.
Hello, Watson. You can see now?
I can recognize people, analyze images, and watch movies.
Well, I wrote a few books. I did a speaking tour.
I've been helping people plan for retirement, and I help doctors identify cancer treatments.
Is that all?
I've recently learned Japanese.
Yeah, I was being sarcastic.
I haven't learned sarcasm yet.
I can help with that.
It's a little bit tongue-in-cheek, but it's actually a very good 30-second summary of what's happened in the last 5 years. Watson has been learning a lot of skills. Skills for analyzing a financial portfolio, skills for looking at options for a doctor of different subspecialties in medicine, decision support systems for very senior kinds of decision makers in various kinds of companies, starting from executives who do mergers and acquisitions, all the way to people who do sales. So pretty much every capacity, Watson has been enhancing cognitive processes. Think of them as sort of business processes that have cognitive elements in them. How has Watson enhanced elements of those business processes or tasks that are especially cognitively challenging and that we as humans already have a limitation for, but machines can actually process huge amounts of information in ways that we are finding are very useful for people to learn. And I'm going to give several examples of that. In fact, our ultimate vision is that every single professional in the world will have a Watson as a cognitive assistant, helping them do their job. Whether you're from healthcare or from financial services, education, or you're a business person in any organization, any company, we think that you could have a Watson on your shoulder, so to speak, that's whispering to you, right? What is your best option, or what are the options available to you at any given moment in time as you're making decisions throughout the course of your day? So that's kind of the vision that we're going after. And as you think about that vision, consider what makes a profession today, right? There's literally, if you go to a database of professions or occupations, there's literally thousands of occupations. And in fact, we did that exercise. What does it take to achieve a professional level competence in one of these occupations? There are thousands of occupations at the top, and each of those occupations require a certain level of training, right? So we all go through our education, from elementary school all the way through, graduate school and then professional exams. And in this picture, I've tried to depict a set of tasks that we learn as we go through this process. So for example, this is not the one way to look at this world of tasks, but I think it's a useful way of doing it. For example, we have tasks that require ingestion or digestion of lots of information. Then we have cogitation, where we think about things and reason about things. We generate new artifacts, like, for example, I'm giving you a talk right now, or you might be writing a paper. Those kinds of generation tasks. Interaction tasks, for example, we are asking questions, we are brainstorming. Those kinds of things are interaction tasks. And in each of these categories, you learn things. Like when you're in elementary school, you understand how to use pictures. Or you understand how to learn rules and follow rules. But as you go up in your educational processes, you learn much more complex tasks, such as negotiation. Or if you are a lawyer, how do you interpret the Constitution? Very, very complex tasks, right? But as you look at each of these tasks that we learned, there are some standard performance metrics, right? Metrics of progress, right? Very early on, you have standardized tests, perhaps, maybe SATs for your college. But when you get to professional level, you have, for example, a CPA, right? A certified public accountant, which is a professional certification that says, okay, you are qualified to practice this profession based on certain standards that we've already set for that profession. And every single profession has something like that. Radiologists do as well. So this space of tasks is extremely complicated. And in AI, we've had multiple ways of approaching this level of expertise that we want machines to achieve. There's one school of thinking which says, there's general AI, where you have a single abstraction for intelligence. And once you discover that abstraction for intelligence, everything else can be learned. Right? This is AGI thought, which many people still dream about. And of course, there's many groups that have bet their careers on this. Somebody might say, deep reinforcement learning is that one technique with which we can do all of these tasks, right? But the approach that we in IBM are taking as a group is that intelligence is likely to be a portfolio of different technologies, different algorithms, different processes that we don't even know what that full set is yet, obviously. Neuroscience is very young, AI is still very young, and I think we're still discovering how the processes of intelligence work. And over time we will. But while we are discovering those processes of intelligence, we think we can make progress with certain very important practical problems that are relevant to businesses, to the world, and where we have a business model, so to speak, right? So how do we achieve that? We achieve that by basically picking the most valuable professions where people need this kind of support and building a slice through this entire task set. So you can imagine that if you're a radiologist, right, you could use help for maybe interpreting images for anomalies. That's a routine task that you can delegate to a machine. But then I think there was a question asked that was exactly the right question in the previous discussion, which is, what is the role of the doctor? The role of the doctor there is to establish a protocol, a system of trust, so that you can understand what the needs, your social and psychological needs, as well as personal needs of a patient are, make some judgments, make some value judgments, use a lot of common sense, and then provide the right treatment approach that is relevant for that particular situation. And that requires so much other knowledge which is not embedded within the machine's decision-making process. And I'm going to give you several examples of this, by the way, but that's the principle that we are following. And you can imagine, not just for radiology, you can look at finance, right? Accounting. There's going to be tasks in accounting that can be very easily automated using AI techniques. And you can think of another slice through this. And you can go all the way back to mathematics, right? I mean, you can build statistical models very easily. You can build some certain kinds of predictive models. And that's another set of tasks that you can learn. And so on and so forth. But as you build these hundreds and thousands of these slices, you can kind of imagine the stem of this tree broadening. And that stem kind of represents the more fundamental processes of intelligence and tasks that we all need to do regardless of which profession you pick. And what we've been systematically doing in our group is to find those capabilities that are at the bottom of this hierarchy and make them available as cloud-based API services that anybody can build on top of. And it's called the Watson platform today. It's not just the one monolithic system that was built for Jeopardy, but it's a decomposed set of capabilities that's now available on the cloud for anyone from any one of these professions, not just IBM. It's, in fact, literally we have tens of thousands of people building applications on top of the Watson platform using the core capabilities that we've discovered at the base of this hierarchy. But of course, as we go higher and higher up, there's more value from a business standpoint, and that's what people buy at the top of this hierarchy. And that's the bet that we're making in IBM, that this set of cognitive systems is going to transform pretty much every industry: healthcare, financial services, education, even government. And you name it. Manufacturing, I think there's going to be a lot of it where there's a lot of physical world required, but there's a lot of professions where it's much more on the mental or the intellectual world. So that's the approach, and I hope that that makes sense. And I want to pick one or two industries just to give you a sense of how we're approaching this. So if you think about medicine, when you look at the totality of data that's available, it turns out that the classical healthcare data only represents about 25% of all of the data that's relevant for providing the right kind of healthcare. The rest of it, like your social interactions, your stress levels, your food habits, your psychological state, those kinds of things are not even digitized. And in some cases, when it's digitized, it's not available to the medical systems, and that probably determines a lot of how to treat any individual. And because it's dark, that data is dark, and it's not available to medical systems, I think we are running a big risk. We are actually, we are not successfully treating many conditions. We are worried that, in fact, we're losing an opportunity of treating our patients correctly, treating educating our children and students appropriately, and so forth. And it's also based upon just the amount of data we have. We talk about the raw data, and I think somebody else made the point earlier that it's not just the raw data which is growing exponentially, but it's really the knowledge that you need from that raw data that will eventually help you make the judgment calls, right? And what does knowledge mean? You take the raw data, you extract features, you link the domains, and you eventually come up with a contextual analysis, and you represent that contextual knowledge in a way that can be interpreted and reasoned with by a machine. That's what is eventually going to help us get to the level of expertise that professionals will care about. And if we don't get there, we are paying a big price, as I said, right? It's not only about healthcare, where we can see very clearly that people are not getting the best treatment just by looking at the number of errors that happen. You look at education, I think we're pretty far off with respect to personalized education or with our environment. So we believe that having these cognitive computing systems are going to be as essential to decision making as having search engines are to doing basic information retrieval. So we think that every industry should start looking at how to use cognitive computing in their own business processes. And many of IBM's clients have started doing that. And I'll give you a few examples. So one of the most well-known examples is the work we've done in cancer treatment with Memorial Sloan Kettering Cancer Center. There's actually also a very interesting 60-minute segment that came out a month or two ago about our work with the University of North Carolina, Chapel Hill, where there is a tumor board that has Watson as one of the board members, so to speak, and it's providing a recommendation for what kind of treatment options to use. In fact, I'm going to show you how that particular instantiation of Watson works. We have examples in which we've shown how diabetics can use Watson to get some kind of advance notice for how to behave, what to eat, what not to eat, and so forth. and that's productized by Medtronic now. We have Sesame Street that is looking at using Watson question answering as a way to engage kids better. We have a company called Local Motors, which is using Watson as a tourist application. Where when you travel in the bus, you have Watson available in the bus. You can actually have a conversation and say, okay, what are the interesting things around here regarding theater or whatever it is that you're interested in as a tourist. We also have sports applications that people are building, like US Open, where you can be a spectator in the audience. You download the app and you ask questions about a particular sports person or an event in sports that's related and things like this. And very recently, we also created, semi-automatically, a trailer for a movie. So the original movie, is analyzed by Watson to identify what are the segments that have very significant emotional, relevance and content. And there's a small number of those that get sequenced in a particular fashion and provided to a designer who then makes some final decisions. It's not fully autonomous, but it is going from a couple of weeks to a couple of hours. You can put together a trailer that makes sense to people, and you can watch it on YouTube and see what you think about it. So all of these applications are commercially available today, and these are built on top of what I said earlier, something we call Watson Platform, which has more or less this kind of a structure. It's a number of capabilities. All of these hexagons are kind of basic capabilities which are more towards the bottom of the hierarchy that I showed earlier, things that we all need for most of these applications. So in fact, all of those examples that I showed earlier are all built on this platform. So the applications are built using some subset of these capabilities, and you compose them in different ways for different applications. And then there are data sets underneath, there are models underneath, which is on a cloud platform. So it's, the idea is to provide it to as many people as possible, as many businesses, students. In fact, there are many students in universities around this country and around the world that are using this platform for teaching what it means to build cognitive applications going forward. And how do you build these applications? You can, for example, I picked two simple examples here. One is personality insight. So if you provide, there is an API to which if we provide a piece of text, it can actually identify what is, likely the personality type of the person who wrote that piece of text, such as, are you open or closed? Are you, optimistic in general, or are you not, right? Cynical, right? That kind of thing. So there's a whole big five analysis of personality that is given to you. Now, that's a very simple capability that's available in the cloud right now, but you could, in fact, use it to do much more complicated things. Like, for example, there are researchers in our team who's looked at language use by individuals to determine the state of mental health of individuals. For example, mild cognitive impairment, right? Or some kind of schizophrenia, right? These kinds of things can be seen in the way people use language. And there are publications available today about how specific structures of words and patterns of words that are used indicate certain conditions of mind. And that can be, diagnostically very, very important for, in fact, the largest category of diseases we have today, right, in the world. Similarly, on the right-hand side, I show visual recognition, which is a standard sort of image recognition kind of a problem, which you can imagine doing it for a consumer-oriented application, like looking at Pinterest data and figuring out somebody's hobbies. Or you can use it for taking a picture of your skin and deciding whether a little scar you have in there is melanoma or not, which we've started to do as well in a medical application. So this, this consumer level and some very serious health level applications that are possible using the same underlying components, which needs to be, of course, specialized for the specific domains, and I'll talk about that. So behind these kinds of capabilities, there's actually an entire research agenda that we are building right now in my team. And I want to tell you just a little bit, we don't have time to go through it completely, but I want to just give you a sense of what does that research agenda look like? Fundamentally, there are 3 levels in that research agenda. So there is a mid-level, which is all the core capabilities which shows up as APIs, like machine learning, knowledge acquisition, visual comprehension, and all of those things right in the middle over there. Those are what I call core capabilities. And then there are applications or solutions on top, which are things like dialogue or certain kinds of research and discovery, which I'll show you an example of. There are educational applications, there are healthcare applications, all kinds of applications on top that we are building and exploring the whole space of. And at the bottom, we are also optimizing the algorithms for new hardware and all the way down to device level physics, basically, right? So, at the hardware level, we have new kinds of architectures like neuromorphic systems. Down below at the device level, we are creating new kinds of devices like resistive processing units, RPUs. And of course, we also have a program in quantum computing that we're exploring how these particular algorithms can actually be optimized on various kinds of devices. And I don't have time to talk about the entire research agenda here, but I just wanted you to be aware that there's a very broad and a deep research agenda around cognitive computing that we're currently pursuing with some universities. What I do have time to do is to show you a couple of examples of the outcomes of our research. So let me show you maybe 2 or 3 examples, and then we can just step back and look at the implications of this set of systems on work in the future. So the first example I'm going to pick is radiology, specifically the radiology of breast cancer. And imagine a radiologist of the future having a tool like what I'm going to show you available to them to get a lot of the routine work done at higher accuracy at lower cost, and provides a set of differential diagnoses or options for decisions that the radiologist, along with the physician, ultimately has to make based upon the condition and the situation with the patient. Now, the one thing I want to mention very clearly up front is that radiology is not just about interpreting images. It's about, first and foremost, understanding the basics of medicine, right? Anatomy and physiology, which you go through in medical school. So that's a set of knowledge that you have to know in order to interpret what's going on in the image. And then you have to understand the specific patient's longitudinal data, meaning what's happened, what are the episodes and encounters they've had with doctors before, and what's happened previously. This example I'm going to show you is going to combine the image processing with the knowledge representation that comes from textbooks and the longitudinal data processing that comes from patient records, electronic patient records.
Ultrasonic image has arrived. Tumor detection. Tumor has been found. Proceed to tumor characterization. Shape detection. Oval. Mass margin. Well-defined border. Circumscribed mass. Orientation of mass. Parallel to skin. Lesion boundary. Echogenic halo. Echo pattern. Anechoic. Posterior acoustic features. Posterior enhancement. Mears parameters. BIRADS2. Anechoic. Homogeneous. Get clinical input from the patient files. High fever. Mastodynia. Tender left breast lump. Combined recommendation. Differential diagnosis. Either simple cyst or galactocele. Patient management. Favor course of antibiotics over fine needle aspiration or incision and drainage. End of case processing. Thank you.
So this is a simple example where the choice of options is pretty dramatic, and having a decision support system that provides a certain level of confidence towards one decision or the other can be a huge benefit to radiologists. In fact, when we showed this kind of a system to the Radiologists Association of America, I was worried that they would be telling me you're taking our jobs away, right? But it turns out that this is welcomed by them with open arms. And there are many reasons for it. One of the reasons is that there are only about 200,000 radiologists in this country. But the demand is about 1 million, for about 1 million radiologists in this country. So the idea of demand is something I want to come back to, or elastic demand, meaning what are the new kinds of needs that we need as a society? And will these systems give us some new ways of dealing with those needs, right? It's not just about what's it going to take away from us, which is all the jobs, right? The current jobs, or the current tasks, but what are the new things that it's going to give us because of the need? So think about the 200,000 radiologists versus the 1 million radiologists that we really need in this country, and the cost of radiology. And I'm not even talking about all the remote areas and the developing world where there's going to be no support for such a thing unless we have a way of delivering it electronically, right? So there is a need, and without having technology like this, I don't believe we can even meet that need, or we can even start thinking about it. So, I look at it as, contrary to what many other people say about, the problems with, the economy or the workforce in the future. I look at it as, we need more AI so that we can unleash the new demand. And I'm going to come back to that point over and over again in each one of these examples that I'm going to show you. So the second example I want to show you is in the domain of cancer research, not treatment, clinical treatment, but research. So all the way back to when you look for what kinds of drugs, what kind of protein pathways are required, and so forth. And that's much closer to my heart as well, because I'm a researcher at heart, and many of you probably are similar. I just want to mention that even in this example, there is a knowledge structure. This is not just about deep learning, pattern recognition, perception of the image. There's a knowledge structure underneath, and the knowledge structure is very complicated. And there's many different kinds of relationships among the concepts that we are worried about. Like, for example, in this case, I'm showing a TP53, which is a gene that many people understand, or understand as being central to many kinds of cancer. And there are many other related concepts where the relationships are very complicated. Like, there's a tumor suppressor, there's an inhibition going on, there are some potential drugs, there are some causal relationships, and so forth. Now, these kinds of relationships are still very difficult to represent in computers and then have reasoning algorithms on top of this, but that's what we are dealing with. And we have a version of this available right now, even within our medical systems, but there's still a long way to go. I mean, this is just the beginning of the field of knowledge representation and reasoning, but I want you to keep that in mind as I show you the next example, where the scenario is there is a cancer tumor board that is determining what would be the appropriate treatment to make for a biopsy that has been already sequenced, and now they're trying to figure out whether there's any drug available at all for that particular pathway that is already mutated. So that's the scenario that we're going after. So here's an example, and I'll just talk you through it. So imagine that the mutations have already arrived into your research facility, and here is a standard representation of the 23 chromosomes, and you can see some of the mutated genes, which if you're a genome scientist, you'll understand all of those. Now, it shows you the pathways of the mutations, and there are a few things that are going on here. So when you click on the mutation button over here, it shows you which are the pathways that are affected by the mutations. The second button here shows Watson. So when you click on Watson, what it shows is some connections between these kinases that were not apparent to existing literature, but Watson has actually gone through Medline and found new relationships, right? And this is the part that was shown in the 60-minute segment. So you'll see some new relationships, and now you can click through and go into what are those new relationships based upon, right? Which clinical trial happened? So you can go deep into it, and you can see, what kinds of experiments were done, and you can go all the way and you can examine the evidence behind a new linkage that was made in that kinase picture. And then when you come back here and you say what kinds of new drugs are possible for the newly discovered dotted line that you see there, there are some new drugs that showed up. And it turns out that these are drugs that were off-label. They were not originally available for treatment of the original mutations, but they were for some other set of cancers because cancers have been organized by organs as opposed to the actual mutations, right? So unfortunately, and that's changing slowly, thankfully. And so you can eventually see that the tumor board can get a report from Watson or this decision support system that says, okay, so here are the gene mutations that we saw, and it scrolls down and it goes all the way down to what are the recommended, let's let it go down. Yeah, the recommended drugs for, and what mechanisms of action and what kinds of status is it. So in one case it's approved, there's another case of the drug still being investigational and so forth. So this kind of a report available at tumor board along with doctors is tremendously useful. And that's the substance of that 60 minutes that I mentioned earlier. And there is a publication on this topic that is forthcoming. But I just want to give you a sense that for cancer researchers, this can be a tremendous tool. And we've just deployed this to the New York Genome Center, which is a conglomeration of cancer research hospitals. I think there's 15 or 20 of them right now, and it's growing. All right, so 2 examples that I gave you in the field of medicine. I also want to just for the sake of discussion, want to go into a different field, which is not medicine. And I want to show you a kind of a financial scenario where there are senior executives in a company that are looking to acquire another company, and they're looking at many different elements of a company that they want to acquire. And that's a complex decision. Turns out in IBM we do that regularly, and we're internally using this kind of a system today to do this. So think about Watson as being a member in a boardroom where these kinds of hard decisions are being made.
Watson, show me companies with revenue between $25 million and $60 million pertaining to analytics.
Let's see what I can find. I found 87 companies.
Nice.
Okay, so that's a good start. What do you think, Brian?
But I was doing some homework, actually. I think we should pull in that Watson Strategy Group document. There's a lot of key concepts in there. Let's feed it to Watson.
All right. Watson, please regard this as cognitive strategy.
Watson,
That's
show me
language
companies
processing
with
right
revenue
there.
between $15 million and $60 million pertaining to cognitive strategy.
Let's see what I can find.
Yeah, this is nice.
I found 112 companies.
Now we're getting a lot in here. And we can see we're getting some connections too, I think.
Watson, show me companies that are about analytics and cognitive strategy that are most similar to the companies named Wolfram Alpha and Kawasaki Robotics.
I found 3 companies similar to the ones you specified.
Beautiful.
Well, let's see what we think of these.
Dive a little deeper. Let's compare these things.
Sure. Watson, show me a decision table.
Here is a decision table that will enable you to compare companies side by side.
Okay, but I think we need a little more than that. We need some other attributes. Watson, place the attributes named revenue and employees and corporate structure in the decision table.
Okay.
All right, so now we've got this side-by-side comparison. What do you think?
Yeah, I think that's right.
Watson, give me a suggestion.
I have a suggestion.
I stopped there because, as I always say, it's got a little confidential there. So, but I think the point is that in the limited time that executives like that would have to make a complex decision, they would be limited usually to a research assistant or 2 who will make PowerPoint slides and show them some data, and they have to make a decision based on that. Instead, what if Watson was available to you for making your complex decisions in your boardroom for the domains that you care about, which is the highest value for you, right? And we are beginning to use this, as I said, in IBM. At the end of the day, I look at the interaction between a machine like Watson and people like you saw in this video as absolutely crucial to making this whole thing succeed. Because, as I said before, neither the people nor the machine will have all of the capabilities, the intelligence capabilities that you need. And so if the way I think about it is, there's many scenarios in which the machine is going to be really great at detecting anomalies, doing some large-scale population analyses, doing some bias elimination, those kinds of things. But people have to come into the picture for the realistic applications where you need value judgment based upon things that are not codifiable. You need a consideration of what is the social benefit or compassion. I'm just picking a few examples here, but there's a list of things. Creative problem solving is something that is still very hard. How do you do the job of an entrepreneur or a CEO if you're a machine, right? You need a lot of common sense and many other capabilities that I think are very much on the human side. But if you combine the two, we think you can really transform many, many kinds of jobs. So this is kind of the vision that we're going after. And I was at the Frontiers conference last month at CMU, and Manuela was there as well. And President Obama's OSTP, Office of Science and Technology Policy, arranged it. And President Obama was there, and he joined us for a few of the panels. And he made a few comments, and if you haven't seen his Wired editorial, it's really well done. But he made a few comments at the conference that I thought I should share with you. He couldn't have said, I couldn't have said it better than him. So here he is. He talks like a geek.
How we think about the interface between humans and machines, I think, is something that I know Joyce thought a lot about. This is where the idea of extended intelligence makes a lot of sense. It also is probably the better way of thinking about it for our economy and jobs, because people worry that, well, are we going to get into a situation where a machine's just doing everything? And one of the promising aspects of AI is it turns out that, for example, even in playing chess, a computer with a human oftentimes can do better than just the computer. Well, think about that application broadly to a lot of disciplines. What we want to be able to do is develop systems that are open enough, transparent enough that human judgment, human imagination, creativity are still intruding, are still active, but a lot of the routine stuff is happening day to day. And in some ways, that's just analogous to, how we use calculators, right? It's an extension of our intelligence.
I couldn't have said it any better, right? So, when you think about jobs that are going to require this, more and more capable machines, I think the wrong way to think about it is that the job is eliminated. In my opinion, the right way to think about it is that there's new demand that's being created. And so I want to talk a little bit about this notion of elastic demand. Think about the old days when you had, people in, what are they called? Licensed practical nurses, right? They were, considered to be obsolete at some point in time when technology happened, right? But it actually is the case that there were more licensed practical nurses that were hired in the last 30 years since that was proclaimed. Same thing with tellers, right? Tellers were thought to be obsolete after automated teller machines. But guess what? Tellers have now been redefined to be relationship managers. And it turns out that the number of tellers hired into the workforce is more now. There was, you see the solid line over there is the number of people who were occupied or who were employed as tellers, and the dotted line shows the number of ATMs. So when the ATM numbers went up, there was a slight dip in the transitional phase when people tellers were laid off. But then it turns out that the number of people were rehired for a different job category that leveraged their experience with banking and enhanced their relationship with customers. So what I want to argue is that demand is going to be generated elastically in many different fields that we can't even imagine at the moment. And in order to think about that, we need to think more about tasks and skills required as opposed to qualifications for jobs. That's how I would like to think about it. When you think about tasks for skills, I think we have to come up with new ways of educating people for new kinds of skills. For example, here's a P-Tech school, which IBM has been involved in creating. We created it about 5 years ago, and we're just getting the first generation of kids out. It's a 6-year high school program, which is a vocational program for teaching specific kinds of STEM skills, which are extremely in demand in the economy. And it turns out the first few graduates have just been employed by IBM in new kinds of jobs, which I don't know that I would have guessed even 10 years ago, right? So I don't know what a digital commerce specialist does. But I think those new kinds of job categories are coming up, and these folks have just been hired into IBM to do that. And the good news is that there's a number of schools like that. So 2001 we had one in Brooklyn, but now in 2016 we have close to 60 such schools which have vocational education programs that are longer periods of time, like 6 years, that can generate that middle part that Vijay was talking about, which is not highly skilled, and neither is it high school or less. It's in the middle area where you need vocational skills that are relevant to the market. And the last thing I want to mention is that while we do this, there is a number of social and ethical questions that we have to address. And there's a white paper that we've just written, so I would welcome you to look at this. I don't have time to go through each one of these things. It's written down in the white paper. I want to leave you with this one last thought, that those of us in the industry, specifically 5 of the major players in the AI development industry, that is Amazon, DeepMind, Google, Facebook, IBM, and Microsoft, we just announced a couple of months ago a partnership for AI for the benefit of society. And we are going to be developing best principles for ethical AI. We're going to be developing a lot of material for educating the public on AI. We've just started this work. And we had a panel at the same conference that I mentioned earlier from the president, where we discussed what would be some of the first few steps that we want to take. And we think that such societies that can, or partnerships that can involve everybody in academia, in the industry, in scientific organizations are going to be essential. So at the end of the day, I think this is going to be a time that we should not fear. It should really be something that will change the human condition. I think we should go full force. In fact, we should do more AI than what we are doing today. Thank you very much. I think we have time for 1 or 2 questions, maybe?
Yeah, we have time for 1 question.
That was really interesting. I have a question about the cancer diagnostic tool that looked like the ultrasound add-on. I was wondering if that is actually in use, if it's been FDA approved, and also how does it analyze? Does it use data from previous clinical trials, or do humans just decide numbers to put in for boundaries, or?
Yeah, so at the moment, Watson Health is releasing a number of such products which are all going to be considered FDA Class 2 devices. They are going to be completely reviewed by FDA. And that specific example that I showed you is not yet commercially available, but it probably will be. Something like that will be available in 2017. And when it comes out, I can tell you more specifics, but in this specific research experiment that we did, we had about 10,000 or so radiology images that was used in the training part for the image recognition only. And then there was a huge amount of knowledge engineering that happened for the right-hand side of that picture, where all of the clinical parameters and the anatomical parameters were analyzed. And then there's a whole amount of data engineering that was around the longitudinal records that you saw for the patient record management stuff. So it's a combination of technologies, but they're all trained using MD level skills. that are now part of the team that is building this. And we also have collaborations with hospitals that are providing the data as well as the expertise required to build these kinds of tools.
Thank you.
Okay.
Thank you again.
Thank you.